All right, this is the definition for a limit of a function that's approaching infinity. So the difference here is we start the same, but the then statement has changed. Instead of us finding the distance between the function and its limit being less than a very small number, we're showing that the function value goes extremely large. The function value is larger than a very large positive number n. So let's say that we want to prove this. We're going to start with a preliminary analysis, much like the other problems, but it'll change a little bit. Okay, so step 1, you're going to have the distance between x and 2. And that is the same because it matches, the definition matches the same as the linear examples, when it's not infinity. Step 2 is going to be different. This is where we had the function minus the limit. We're not going to do this minus infinity, but we are going to start with this. So we're going to consider the function. And we're going to go ahead and jump to the final statement. We want this to be greater than m. Now what we're going to do in step 2 is try to get this to be absolute value x minus 2 on this side. So we've got a little bit of work to do. First, I don't want this in a fraction. I want to move this to the top. So we're going to do reciprocal of both sides. Now, if you do reciprocal of both sides, it changes the inequality. So instead of greater than, it's now going to be less than. And an example of this would be if we know, for example, 2 is less than 4, and I were to do reciprocal of that, 1/2 and 1/4. Well, 1/4 is less than that, so that is why the sign flips. So we're not quite there yet. I want to get rid of my square, so I'm going to take the square root of both sides. When you take the square root, the symbol is still the same, and you can test, like I did over here, you can test a little example to prove that to yourself. But the weird thing here is we need m to be positive, so we are just going to go ahead and plop in absolute values there because we didn't know what was inside there, but when we squared it, it was always positive. So in order to keep it positive, we can just put absolute values. And here we are. We got to where we wanted for step 1. So this is my delta. That's your step 3. Whatever we end up over here. Whatever we end up with. All right, so now that's your preliminary analysis. Now we're going to actually go into the proof. Okay, so given that we're going to say m is greater than 0, because this is a very large positive number, because it's positive infinity, we're going to choose the delta that we have down here. Okay, now we're going to start our if statement and work our way to our then statement. So if x minus 2 absolute value is less than delta, then... Now, usually we would jump to our function, but what we're going to do is we're just going to work with x minus 2. So everything we did here, we're just going to go backwards. We're going to go backwards because we started with our conclusion, and that's where we want to end in the proof. So we're going to manipulate this. X minus 2 is less than delta. I can square both sides. So I can say x minus 2 squared, which is always positive, so I don't need the absolute value anymore, is less than delta squared. I then can change it into a fraction. So I can do the reciprocal of both sides. But when I do that, remember the sign flips. And then you should get to your function when you're done manipulating. You should get back to your function. So at this point, there's nothing left I can do except for to substitute in my delta value. So that equals 1 over, substitute in your delta, and it's squared because that delta is squared. Then your square cancels your radical, and then you can do the reciprocal to both sides. So we get m, and that is what we wanted to prove. So we just showed that the function, which is this, is greater than m. So we're now at our conclusion, therefore, by definition, and then we just restate our limit. The limit as x approaches 2 for that function is infinity.